So everybody, welcome to Dean's Distinguished Lecture Series. I'm Marty Hurst, Dean of the School of Information. Before we start, I have to make the little statement that this is being live streamed and recorded and may be posted on the web. If you ask any questions or make comments, they may be included in the live stream and recording. All right, now that that's out of the way, it's my great honor to introduce our guest today, Professor Alvitta Ottley. She's a prominent researcher in the information visualization community. Her research uses interdisciplinary approaches to solve problems such as how to best display information for effective decision-making and how to design human-in-the-loop visual analytics interfaces. She's an associate professor in the Computer Science and Engineering Department at Washington University in St. Louis. She received her master's and PhD degree in computer science from Tufts and her bachelor's in CS from the SUNY at Plattsburgh. She's the director of the Visual Interface and Behavior Exploration Lab and holds a courtesy appointment in the Psychology and Brain Sciences Department. I'm envious of that. She's received a lot of awards, including the NSF Career Award and a bunch of Best Paper Awards. And she's going to talk to us today about visual analytics. So please join me in giving her a warm welcome.
Thanks, Marty, and thanks for having me. It's such a great pleasure to be here. Yesterday the weather was a lot better, and so I was glad I was able to enjoy it and get a nice reprieve from the winter in St. Louis. And even today is better than St. Louis weather. So I'm really excited about the talk and all the conversations I've had and going to have for the rest of the day. Today I want to talk a little bit about what I think is a possible future for visual analytics. So I want to talk about a future where AI doesn't serve as a replacement or as a simple tool, but as a collaborator as people explore data and make decisions with data. Before I talk about the future, I want to give you an idea of where we are now with visual analytics. So visual analytics is the science of decision-making with using visual representations, and the community has a particular focus on tasks where neither the human nor the computer can solve on their own. So these are scenarios like in scientific discovery or in national intelligence. In fact, the visual analytics community was born out of this report that was produced by Homeland Security, somewhat of a response to 9/11, where they felt that they needed more interaction with data and more analysis of that data that they had. And many of these accomplishments in the visual analytics community have been made possible by tools like Tableau, Power BI, and custom data visualization toolkits like D3. But the goalpost is constantly moving. And for one, the people that we're creating tools for is shifting. We're not just creating tools for scientists anymore, but this might be a tool for someone at home looking for houses and having to sift through lots of data on the internet to try and find the right home for themselves. By the way, all of these images were co-created with ChatGPT, so you might see some weird artifacts in here. And even if you think about using tools like Tableau and Power BI for data analysis, this can still be overwhelming just because of the size and complexity of the data set that the data that is continuously growing. So this is where the challenge and the opportunity lie. And I think this is where AI can step in. If you think I'm going to talk about ChatGPT, you might be disappointed because that's not what I want to talk about. But instead, I want you to imagine an AI that learns from your interactions with data. So every click, every hover, every query that you make teaches the AI something about you and your preferences and your analytic strategies, and it helps you and even makes you aware of the blind spots that you might have. But this is easier said than done, and there are several challenges that we will have to tackle before this is even possible. And so throughout this talk, I'm going to dissect some of these challenges and discuss some of the existing work that we've done in the biz community and also in my lab, and also some of the paths where I think we need to continue going on. So a simple version of the scenario here is you have on one side the human analyst that is interacting with a computer system, they're exploring the data, and you have an AI that might be observing these interactions and learning from it. This can create somewhat of a feedback loop where as the AI learns, then it can also update the visualization based on what it thinks might be, what it thinks might be helpful for that specific task. And there's a lot that has to go in here. So I'm going to just break down some of the top challenges I think that we need to accomplish. So, I wanted to say that in the long term, this is not just about making predictions, but ideally you have a system that can understand context and the queries and these nuances. This is a long-term journey, but you never know, like we'll see how far we can get. So the first challenge that I want to point out is this ability to predict people, and humans are messy and can be unpredictable. So the question is, how do we quietly observe interactions and learn from them? The next challenge is about this feedback loop. So if you are successful in learning someone's interest, how then do you interact with them? How do you manage these interactions? How do you manage this collaboration? And how do you communicate back to the human what the AI might think or might be helping them with? And then finally, we need to develop some theoretical models to understand, to better understand this collaborative potential. So right now, and I'm going to show you later, in the Viz world, we kind of see the AI or machine learning as more of a tool and not an active participant. What if the AI is a collaborator? What does that mean? What are the ramifications? How do you trust? How do you deal with trust and ethical considerations and stuff like that? All right, so I'm going to start with challenge number one. And humans are indeed unpredictable, but this statement usually doesn't consider the context and the environment what we're talking about. So I want to give you so I spend a lot of time thinking about how people are different and looking at individual differences that would impact how we search and use visualizations. I'm just going to give you a highlight of one of the projects that we did. So this is a project that was in the collaboration with the Laboratory of Analytic Science at NC State. And we wanted to understand specifically a personality trait called locus of control, which defines how in control you feel of external events. We wanted to see how locus of control impacts how people might solve a more complex problem. So we had about 30 intelligence analysts. So they were they were Navy reservists. And we gave them this task, which was from the VAST challenge of 2014. And the VAST challenge is an annual challenge that we have in our community that is meant to provide data sets and tasks that are inspired by real world scenarios. So for this specific challenge, there was a kidnapping that happened, and you have lots of employee communications, and the goal here is to, search through these communications to understand and build this terrorist network and try to figure out who did the kidnapping and where the victims are being kept. And so they had like a really simple interface, and we collected the interactions over 2 days. So here they can read all the articles, they can look at resumes, all the employee records, they can do filtering, and this is like a list of all of the filter results. And then they can use the sketchpad to kind of build out. They also had a separate notes section, but this is like a basic interface that they had. And yes, we did see differences in locus of control, and that's not really what I want to focus on right now. But what I wanted to point out is that while we were looking at this data, we kept seeing these patterns. My highlighting is not working, but we kept seeing these patterns where we see people just interact with a set of documents over and over in sequential order. No, it's not working. A set of documents over and over in sequential order. And it turns out that these documents mapped to the first, second, fourth, fifth documents that were default on the interface. And so this is an example where the interface that we had is what was influencing people's interactions. And this is true for a lot of visualization tools. It seems like I have a video this point. This is true for lots of visualization tools because when you have a visualization system, the environment is controlled, the space of possible actions that you can do are controlled, and the type of questions that you can ask are controlled. And so visualization and visual analytics provide this really great controlled environment for us to learn from interactions and make predictions about what someone is going to do. So this is not my idea. There are lots of people who have thought about this. And over the years, there are several papers in the Viz community, not enough, but there are several papers that have had this idea of learning from interactions and making predictions about what people are doing. Here, a few years ago, we looked at a paper. We did my student and I, and this is led by Sanu Ha. We had this idea of, all right, we see these ideas out there, we see these individual algorithms that people put out, but there's no real comparison of them. How do I, as a developer, know which one of these algorithms to use? So we surveyed this work. We pulled out 7 of these algorithms. Mainly, we just focused on the ones that either had well-defined algorithm or the code is available. There wasn't a lot of them out there. And we implemented all of them. They're all available now online and openly available. And then we compared them across 4 different user study data sets that were also available online. But in general, these algorithms that exist in the community fall under 2 categories. So they're either algorithms that can predict the next data interaction. So they observe what you're doing, and I see you click on this sequence of data points, and it predicts what the next data point you're likely to interact with next. Or these algorithms fall under exploration bias. So similarly, they would look at the interactions and they would be able to say, all right, I think this person is interested in these data attributes, so high-level data attributes. And I'm going to give you some examples of them. So for instance, there's one paper that was published by some folks at Georgia Tech, led by Emily Wall. And she suggested several ways of detecting bias while you're observing interactions. The one that we focused on is called attribute detection, which is exactly what I explained before. It observes your interactions and then it tries to figure out which attributes in this data set an individual might be interested in based on the interactions. Another one that was produced by some folks at UNC Chapel Hill, David Gotts and his group, is called Analytic Focus. And this was designed for a text-based data set. So it's looking at your interactions with text data. And from those documents, it then tries to figure out what are the topics of focus the topics that someone might want to focus on. So this was mainly meant for text documents. So here I'm giving you 2 examples. One example is looking at people's biases and trying to figure that out. Another example might be looking at the topics of focus and then recommend other text documents that are in that specific topic. There's some that do both, and 2 of them are produced by my lab, so I'm going to go through some of these examples and give you a better intuition of what these algorithms do on a lower level. So the algorithm I want to talk about, it's a hidden Markov model approach, and it was designed to track attention while someone is using a visualization. And the way we do that, this works for any given visualization. You can deconstruct the visualization into its low-level features. So for this specific setup, for instance, you have a color, you have the size of a circle, you have the position of a circle, and you can extract all of these low-level features, and that then we use that to describe our hidden space. You can ask me a question if you have, but I'm not going to go into many details about how to specify a hidden Markov model. But at a high level, you need 4 things. You need to define these hidden states, and the hidden states are in this scenario are the space of all possible visual features that someone might want to pay attention to. You need to define the observations. So this can be mouse click, mouse move. So these are the things that we observe from the user. And then we need to define the dynamical model, which then how does attention change over time? And we use work from cognitive psychology that suggests that people's attention at time t is not going to change drastically at time t+1. And so we have a similar attention, but with a small drift. And then we need to define the observational model. So how do actions give rise to the hidden states? And so we went through and we made those we made those definitions and okay, let's now talk about how we make predictions with that. So that's like the basic setup, and we still need to make predictions. And the way it works is here I'm going to show you an example with this map. So this is a map of crimes in St. Louis from March of 2017. And here you're seeing dots, which each represents a reported crime, and the color of the dot would then specify the type of crime. So for instance, red means homicide, blue means theft, and you'll see certain patterns here. One is the majority of the crimes here are theft related, so there are lots of blues, and then you see, well, you can't see here, but the least popular crime was homicides for this specific month. So the way we do this, we use something called a particle filtering approach. And the best way to describe this is for me to so imagine that I'm showing you what the algorithm believes. So I'm giving you a visualization that represents what the algorithm believes at any given time step. So this is t=0. We haven't observed any interactions yet. So the algorithm believes that, so you see dots all over the place. The algorithm is believing that someone might be interested in anything, any location, and we choose their specific colors based on the original distribution on the map. So most of the colors here are blue. You might see some circles without a color. That is saying that the algorithm is sure about the position, the location, but is not sure at all about the specific color. So here we're reasoning about the position of specific interest and also the colors that someone might be interested in. And in this map, there were only two variables we need to manage. So here, I'm going to show you a click that might be in a square, represented by a square. Okay. So someone clicks on a red dot and you see the algorithm updates. Every time you observe a click, the algorithm then updates. And here, for instance, the algorithm feels like someone is interested in lots of the red stuff. It's not really sure about the location, but it's kind of sure about the red stuff. You see then someone might click on something that's orange and then it starts updating. Well, maybe that person might not have been interested in all red stuff. This is how the algorithm continues to update every time it observes an interaction. At the end of every time step, what we do is we map these particles back to the map. So every particle, so here we have 1,000 particles, every particle then votes for every point on the map. So for a particle in a specific location, it votes for things that are close by. For a particle of a specific color, it votes for things on the map of the same color. So here, because there are only 5 homicides, then this algorithm believes that people are interested in homicides. And it also believes that maybe they might be interested in a specific location there, but it's not very sure. And so this worked extremely successfully, particularly for simple tasks. So we did an online study and showed that it was like 90-something% accurate at predicting people's next interactions with the visualization. So this is an example of one that sits in the middle because you can both predict what someone might interact with next, but based on these particle distribution, I can also say something about the biases in what you're looking at. The other algorithm that I want to give you an intuition of, this was led by my student who has recently graduated and he's now at Oak Ridge National Lab, Sean. And the problem set up here is, so we want to use Bayesian model selection to track people's interests over time. And the problem set up here is that assume you have a data set that has these three attributes. These attributes, of course, are visualized, but then we make the assumption that someone might be interested. There are several different, we can create different models that would represent people's interests. For instance, one model might say this person, one model might say this person is not interested in any of these attributes. Another model might say someone is interested in attribute 1, but they don't care at all about attributes 2 and 3. Another model might say they're interested in all of the attributes. And so we can enumerate all possible interests, and this indeed can be large and can be computationally expensive, but with both of these, they can be large because we're looking at the combination of all possible. But with visualization, oftentimes it's capped because you're looking at most maybe like 7 features at a time. Because of the limitations of people's perceptual system, we can't just show a bunch of stuff. And so the way this works is that we then reason about, based on all of the observations, we start with some informative prior, and we can reason about the posterior probability of these models based on likelihood. And so this is essentially Bayesian reasoning that we're doing. And this also was fairly successful. But as I said, depending on the size of the data set, it can indeed be computationally expensive. But I want to just talk high level about the kind of things that we observed from comparing all of the algorithms in the community. As I said, we did it with 4 different data sets of different types. So we were limited by the data sets that are available, openly available. So we wanted to use real user study data sets. They're not a lot out there, unfortunately. So I would love to see more people sharing their data sets once they do user studies. But we just worked with what we had. So what are the insights we got? Essentially, unsurprisingly, the models, all of them tend to work well when the task is highly specific and there isn't a lot of noise. And so because a lot of these studies were online studies, some of them were really noisy. And of course, it wouldn't do well when there's a lot of noise. We also created an ensemble model, which took all of the models and had them an average over all of the models, and that performed best. But again, it's costly, so it might not be appropriate for real-time algorithms depending on the visualization and the data set. Yes.
So maybe I'm missing something. Did you fix the interface for all of these data sets? And I would imagine that the benefits of a given model would depend greatly on the interface features and the kinds of interactions that are allowed, or did you not see that much of an effect on?
So we didn't consider the interface at all because we're just looking at the data set and interactions from participants who may have performed in specific studies. Yes, there are differences based on, so for instance, the analytic focus model did well when the data set had to do with text-based data. And that it actually outperformed a lot of them. So the right model depends, it depends on the context, and it's really hard to go through all of these different things. So I would highly recommend looking at the paper if you want to know which model works best for you. But there isn't a single model that is good all the time, except for an ensemble model, because then they all get to boards to some extent. But yeah, that's a great point to bring up. Another thing that we noticed is that when it comes to detecting biases, all of these models to some extent assume that bias exists. So even when we did, so we had to do some qualitative coding to figure out, do we believe that an interaction was biased or not, or do we see evidence of biases? Do we believe that people are paying more attention to certain attributes, which kind of then goes into the, what does it mean to be biased? But even when our coders saw no evidence of bias, all of these algorithms assume that bias exists. And so it always says that someone is biased. And so that is something that we need to definitely work on. But the clear takeaway was that there wasn't any winner, there wasn't any single best algorithm that worked well. It really depends. So this is where we are right now, and it's not a lot. For one, a lot of the techniques that we see out there is made with like geospatial visualization, and I don't know if because it's a low-hanging fruit, because it's easy, but we don't see a lot. There aren't a lot of algorithms out there, and then those algorithms all focus on geospatial visualization. Another thing that I think we definitely need to focus on is think about how do we map low-level interactions to high-level tasks. So I can say you're going to click on this next, but why are you going to click on it? And in order for us to create tools that are going to be potentially collaborators, a collaborator has to understand at a high level what someone is doing. This is hard because even in our community, we don't have good task models. So this is some work that I did with Lilani Bottle at UW and her student at the time. Actually, she was at Maryland at the time. UW at the time. And we tried to look at all of the theoretical models of tasks in the community. So there are a bunch of papers out there that say, okay, here is a taxonomy of tasks. And we took all of those task taxonomies and applied them to interaction logs that we had and that we found on the internet. And none of them really did well at representing what we saw, which is really no surprise because they weren't designed for that. The way these were developed is that someone went and maybe did a review of all the papers and say, okay, here are the tasks that I see in different papers. And it wasn't really meant for represented interaction logs. So we need more work in this space. Yeah, we need more work in this space. Okay, so I'm gonna move on to the second challenge. And the second challenge is associated with how do we then, if we can learn what someone is doing, how do we then use that knowledge to do something? So there's one project that we try to do something with what we learn. This is a project again that was led by Shayan Monajemi. And here we wanted to figure out based on, so we have all these algorithms that can tell you what someone might be interested in, how might we use that, and then can we use that at all? And are they effective in real world scenarios? So up until now, a lot of these evaluations were done after the fact. So there's no real-time evaluation of you observe an interaction and you make a suggestion and kind of see if people use the suggestions. So this is our first time trying to do this. Yeah.
We have about 30 people online. There's a question that maybe fits in here from Nick Greiner. Is there work being done on developing ethical principles for AI assistance analysis? I think about how biases can be helpful for focus, but can also lead a person down a path of reasoning that's unintentionally biased.
Unfortunately, no. So in general, this idea of having systems that make suggestions in real time, there are not a lot of people who are doing this work. So no, unfortunately, we still need to do lots of catch up. So I believe that as we start seeing more systems like these that are making recommendations, then we can then start asking and answering questions about what happens when it comes to biases. But I'm gonna explain this, and I'm gonna tell you something. I'm gonna answer your question a little bit about that. So we developed a system around another vast challenge, and this vast challenge described an epidemic in a fictitious system called Vastapolis. And so you have, the idea here is that, well, the backstory is that there's a bioterrorist attack where there was a truck that exploded in the bridge. Some of the chemicals got in the air, so there are people who were in the wind direction. There are people who are having upper respiratory style symptoms. And then some of the chemicals also got into water. And so there are people who are having gastrointestinal type symptoms. And so the scenario here is that people are now coming to the hospital. And so the authorities are trying to figure out what's going on, what's causing this illness, is it contained? And so here, we build a system that allow people to explore this data, and we saw this as like the first step of people exploring social media style posts to try to figure out who's sick and what. And the idea is, this is the first exploratory step, and they're going to be tagging people who they might want to follow up for contact tracing. So this initial exploration will be passed on to other analysts who is going to then follow up on it. This was co-created, co-designed by folks at their laboratory analytic science as well. So we work closely with them to design this and design realistic scenarios that would make sense for them, and also interfaces that would make sense for them. So with this, we use, so here I'm showing you, we have lots of tweets and we have geospatial tags for these tweets. We use word-to-vec algorithm, and we're able to then reason about the similarity based on the interactions that we observe. Okay, I'm gonna wait until the end. I was gonna try to see when I could fit in the answer to that question. But so we build this algorithm that makes suggestions as people are interacting with them. And we did a user study to test if this algorithm is at all effective in real time. So we had folks that we recruited on Mechanical Turk. We had two groups. One group is a control group. They got no suggestions at all. And the other group is the active search group. They had suggestions, and this is there's lots of data in this data set, so we just give them 10 minutes to interact with it and see, we just told them to do as much as they can in 10 minutes. One of the things that we found was that, so here I'm showing you a graph where there's time on the x-axis and the number of microblogs, so number of tweets that is covered on the y-axis. And overall, the active search group, so the group that got the machine learning suggestions, they outperformed the group that didn't have any. So they were way more productive. They were significantly more productive. And here I'm going to show you, I want to highlight something. So we look at the number of hovers per minute. So what are people looking at? It turns out that people in the control group actually hovered on more things. They were doing more work. When you look at relevant hovers, so relevant means that you're hovering over things, you're interacting with data points that are relevant to the actual task. We saw that people in the active search group, so those that got the help, were significantly more likely to interact with points that were relevant. And so here we're assuming that with the machine learning help, they were able to isolate the noise from the things that were actually relevant to the task. So they were more efficient, even though people in the control group technically were working hard. We actually had to go back and look back at our incentive structure, because we realized that it was a little bit unfair after all, because the design of the study is that we paid more for the more things we discovered, and the active learning group had such a more of an advantage, and so we went back and just like paid everyone the same amount for fairness. But But in this study, we found something that was interesting. So here I'm showing you the histogram that's showing you the recommendation usage. So these are people from the machine learning group, those people who got the recommendation. I'm showing you the recommendation usage, and I'm showing you the count in this histogram. So here we saw that there were a significant amount of people who did not interact with any of the recommendations. So even though, and we looked at the accuracy, these recommendations were fairly accurate, but they didn't interact with them at all. And when we asked them, we also had a usability survey at the end, and we asked about trust, whether or not they trusted the recommendations. And those people who did not use the algorithm, that we did not use the recommendations, they were more likely to say that they did not trust the system. So this is an example where we saw that like distrust would affect whether or not these algorithms are all useful. So you invest time in building these tools and no one uses it, like what's the point? And we also saw, I also think that people who just always use the recommendations so well, like that is pretty problematic, having blind trust, because ideally you want to have a healthy level of trust. And so to answer the question, we actually had a follow-up study, and I'm gonna skip ahead because we were looking at would transparency improve trust? So we want to get people to use the recommendations more. There were some issues with this because there are lots of limitations on what the types of explanations you can use in a visualization system because it's already packed with points. You can't really have long explanations. So we're limited in what we can provide as explanations. But also we wanted to actually look into that question of if this algorithm is designed to show you more of what you've already seen. And so if I'm showing you more of what you've already seen, is that going to bias the decisions that you make downstream? So short answer, just based on what we've seen is no. We actually saw the opposite, where people who had, the more you use the recommendations, the more diversity you saw in the data. And I hypothesize that is the case is because you just see more things. And so more things just translated to just a higher diversity of points. It might be different for different scenarios, but that was a surprising finding for me. So in terms of like future work, I think we need to do more work in terms of looking at trust, looking at biases for people and making sure that the algorithm doesn't help perpetuate biases, but also the algorithm itself doesn't introduce biases. There are lots of work with it that we still need to work on. The other thing that oddly is important is this idea of interaction. So not just with these types of studies, but over and over when I do online studies, I realize that there are people who just don't interact with the system at all. So we had a version of the system that will update based on panning and zooming, and so few people panned and zoomed that they didn't update, and there were no suggestions made at all. And so there are lots of failed studies that I've had over the years, and just because I go in with the assumptions that people will interact with the visualization, and naturally they don't interact with them. There are also different reasons for that. I would love to discuss that more because I'm not sure why, but one possible reason is like based on a talk from the deputy graphics director of New York Times. This is back in 2016 when he gave a talk, and they found similar things where they were developing these complex visualizations, and then people, they just wanted to scroll. And so one of the things that was like pretty, that stayed with me from that talk was, I remember he said that if you want to show someone something, you should show them. If you expect someone to hover over something in order to see it, you should assume that they would never see it. And so we as visualization designers need to think a little bit more about how we design and maybe like the cues that we give for interactions, because people don't always interact. And this might be a difference between designing for people on the web versus designing for people who are in a more professional setting, because we don't see that when we look at people who are doing intelligence analysis, but when you look at people on the web, we can't really expect them to always interact.
Yeah, I think that's a pretty common finding, that people don't interact that much, very small percent interact, even with the wonderful New York Times visualizations. I'm wondering if it's like, do you think there might be, you could speculate some relationship between what you go in expecting to do? So I'm reading the papers or the online paper versus, say, if you were in a gaming environment where when you play a game, you don't expect to sit passively and watch.
Yeah.
Do you think that might make a difference?
I agree. I think a lot about the affordances of visualization. And so the visualization is kind of meant for you to like extract information quickly. And so if people go in with that mental schema for what to expect from a visualization, not really to interact. But I think you're also right in that. So you're right about the expectations where you don't go in with the interaction, but then I think also when we design visualizations, we're not designing visual cues. So if I go back to something like this, yes, hovering was incidental, but how do you know, unless you have like a specific tutorial, how do you know I can click on something? There's a button up there that's really small, that's just like I can zoom in and zoom out. But these are like small visual cues. How do we make these things more prominent? How do we make them a little bit more intuitive? And that might go back to like just traditional ACI design, which we need to integrate more of. Yes.
I guess not to go down too far this like speculative rabbit hole, but I would like, do you think maybe there's like a cultural element to it where like in the past we didn't expect for graphics to be interactive, but maybe like as there are more and more interactive graphics, people like feel like expect to interact with them more, and so maybe in the future we do see that everyone just tries to interact with everything and this no longer becomes a problem? Or do you think like there's something deeper than that where like people just by default don't want to interact with things?
I mean, all these are valid. I have no idea. This seems to be like a really cool study, like thinking about when people interact with why. I need to think about that. Like, how do you tease out what makes someone interact with something? Is it a learned behavior? Because you're right, visualization can be seen as an image. And if you view it as an image, then why would you interact with an image other than look at it, right? If you see it more as a tool for exploration, then you might want to explore. So I think all of these things are valid theories. Yeah.
Kind of following up on that, you did some work on like individual differences. Do you think that that has any impact on like interaction? Like, for instance, if somebody like scores higher on like openness or like curiosity measures, are they more likely to maybe interact with that, or like would that have an impact there?
Yes, so there's openness to experiences. There are individual differences that are correlated with like curiosity, and so short answer, yes, I do believe it's possible to see correlations there between individual differences and people's actions for explorations, and there is some work that shows that. I'm giving pause because when we design those systems, when we try to look at individual differences, these systems were either, and it was unintentional, but now I realize that there's a consequence to that. The way we design the system is that a lot of times it was an exploratory system that started completely collapsed. So in order to see anything at all, you need to click on something to see it. And so in a way, we forced people to interact with them. So we couldn't observe any of that. There's a more recent study that I did where even though we forced, you can't answer the question without clicking on it, people still didn't click on it. We did collect individual differences there. I think that I can probably go back and look and see if there are correlations between individual differences we collected and and whether or not they were likely to interact. So, I like that. Yeah. Good question.
But when you think back to, when you think about iOS and the interactions there where you have to swipe sideways and so on, they're hidden, right? They don't actually ever explain them unless you watch a demo or you see someone else do it.
True.
So then there's a question of why do people ever learn how to use iOS tools?
Yeah.
And is it necessity? Is it because they're more natural? Is something else? You know, and why doesn't that transfer? Is it just when people are using the visualization, it's too low
The
stakes?
next TikTok video if I don't scroll. Yeah, yeah. Like, I don't know if like it's just intuitive for you to move your finger and that's how you discover it. That's a good question. I don't know what makes that a more intuitive action. And first, and I mean, now that you've mentioned mobile devices, it could also be that we're now interacting more with visualizations on your mobile device, and so clicking on something just feels different. And it's possible that we need to now design new interaction modalities now that we switch to a more mobile setting. So there are lots of questions related to that, and we probably need to answer that, or we have a bunch of static images.
Maybe related to that, like, are you thinking about like augmented reality where you're overlaying digital information, in real world people are moving and gestures and like how do you findings
I personally haven't looked at it. I know there are some people in this, like looking at XAR, but we're still in our infancy with that. There's some folks at INRIA, so this is a lab in France. And I know they did some work where looking at different ways of interacting with more augmented reality style visualization. But the thing about this community, which is both good and bad, is that it's a small community. And so it's good for a researcher because you have a lot of unanswered questions. It's also bad because we have a lot of unanswered questions. But I would love to see more of that too.
I follow up to all these questions. It seems like there's like a very, very large design space that's constantly increasing in size, right? There's kind of like how you design your visualization and what interactions you chose, what the user is asked to do, what the user wants to do, machine learning, all this stuff. I guess like, is there kind of like how do you know what results generalize and what kind of systematic framework is there to really use generalizable principles?
It's hard to say what. I can say that some of these results, because they've been tested on a lot of like geospatial, and that's why I said earlier that we need to see more work and things beyond geospatial visualizations, because I feel confident that these might work in those scenarios, but I don't feel confident that any of these algorithms might work on a different context. And here, like, there are also limitations here. I've only shown you interfaces that might have a single focal visualization. What happens when you have a dashboard? They're generalizable to an extent, but there's still lots of work to be done to cover a more broader variety of visualization scenarios. Okay. So I'm going to talk about the last challenge, and this is about thinking about theoretical models. So in the visualization world, we have models that might describe how an analyst goes through a thought process. So the most popular one is called the sense-making loop. And here it was introduced by Piroli and Hart back in 2005. And it describes the process that someone goes through as they're looking at data. They're doing a data foraging. So they're finding little nuggets of things that might be of interest, and they put it in a shoebox. And then from that, they make sense of it. So here's a model where researchers are describing how an analyst might think about and solve a problem. We have other models that then incorporate the visualization to some extent, but it still doesn't think about the visualization system doing something. The first model that attempts to do that, this was introduced in 2017 by Sinead et al. And they were the first, to my knowledge, that separated, here's a visual analytic system in a model and here are users, and the visual analytic system can do something. And so here it is saying that it is a framework for providing guidance. And so they're saying that, all right, we can potentially give visual cues, and that's what they call orienting, it can orient by giving visual tools, or it can direct a user by providing alternatives. So this is like the first model that says, all right, the system can do something. This is a mixed initiative system that can act. And so again, this is work by Cheyenne. I'm like talking a lot of what Cheyenne's work. So we looked at this and we're like, okay, this is insufficient. As we're thinking about AI, the visual analytic system actually doing stuff on its own, how do we think about that at a more theoretic level? And we thought about the scenarios of the typical scenario, and here a simple one, you have a human interacting with a system and they can take action. And this seems a lot similar to how we think about AI agents in general. So you have a simple AI agent, they observe their environment, based on what they observe, they take an action. And so based on these similarities between AI, theoretical AI, and Viz, we thought about how then can we use this framework to think about visualization. And for one, it gives us a vocabulary to start thinking about these things. So we didn't have vocabulary for what do you call a visual analytic system that acts? And so, it was very helpful to think about it in this context. And now we can start reasoning about the different types of agents and also the different tasks that a human might be doing. So it could be just interacting based on what you're seeing. So that's a simple reflex is a model-based agent where it has a specific thing that it's trying to accomplish and is following this model. Is a goal-based agent where it's trying to achieve a specific goal. And so potentially this might be a way for us to think about tasks at a higher level, but we're not there yet. But what's cool about thinking about things from an agent-based framework is that now you can think about it from at a multi-agent space. Here now their AI can act. So now we're not just thinking about humans acting, we're just thinking about AI acting. So this from a more, so I'm gonna abstract this out a little bit. Here we have the human agent, and this could be an analyst, this is gonna be a decision maker. This is like very generic. And then you have an environment, and the environment is a visualization tool. It's the models that are underlying that tool. And now we're saying, all right, so now an AI agent can perceive things that happen on the visualization, and the AI agent can take actions on the visualization. The cool thing about this framework is that we can go even beyond that. We can talk about how much knowledge do each one of these have about the environment. We can then also reason about, is it deterministic? Is the environment, do I know what's gonna happen when I click on something? So is it deterministic, is it static, is it dynamic? So we can reason about the properties of the environment. We can also reason about the degree to which an environment is observable and how much that person can see. So in a lot of visual analytic systems, someone can't see all of the data. You're only seeing a specific sample of the data. So the environment is only partially observable. And we can then expand that to how many agents? Are they cooperative? Are they collaborative? And we can really think about all of these high level behaviors. And so I want to like start pushing this idea of us expanding how we think about visual analytics and corporations in general when it comes to AI agents. And also, this kind of brings me to what I think we should be focusing on a lot more in the community is thinking about, can an agent be adversarial? And what I mean by that is we're now seeing tools like this is a snapshot of Zillow where it's recommending things. It's like, oh, this is for you. But how do I know that it's like recommending something that I want versus something that was paid for? You also see this with Airbnb. Like they're showing me only 20 things here. There are a lot more things that are available. How do I know that it is showing me what I wanted to show me? And how do you then think about a setting where the agent is adversarial? And so these are things that we're not thinking about at all in the visible. So I would love to see more of that. So I started out this talk where I said, is it possible for an AI and a visual, is it possible for an AI to collaborate on a task? And I think there's evidence that it might be possible. We've done some work toward that, but there are lots more work to be done. But overall, though, in general, what we're capable of right now is that we've shown that we can, under certain scenarios, we can observe and we can make predictions. I've shown you one example where we're learning data interest and we're making recommendations. Like there are other work that are out there, but I couldn't talk about everything. And I've shown you one example of a theoretical model, but that's just one. Like there's no reason why that should be the only one. And so I'm really excited to see what they produce, and I'm really excited about the conversations that we'll have with you about everything that I've said. At this point, I do want to acknowledge the students who do a lot of this work, also the funding agents, the agencies that fund this work. So I want to acknowledge them, and I am going to take any questions. Thank you.
So I can't remember if you had both the analysts and the Amazon Turk respondents working the same task. But I'm wondering if you could talk a little bit about what we learned from, like, I don't know if it's the right term, expert versus like novice users. So I'm wondering if you could talk a little bit about that. Like the analysts kind of know their job and they kind of like know to click through.
Okay.
That's just part of what they do. But when you give to mechanical turf workers, that's just maybe not their mindset or their scheme.
Yeah, so we've spent a lot of time when we are designing these online studies to make sure that we incentivize certain behavior, which in and of itself doesn't represent the real world. The thing about mechanical turkers is that if you don't incentivize the behavior, they do whatever they want a lot of times. Now that I've switched to prolific a lot, I don't see a lot of that behavior, but it's alarming for another reason. Where I don't think prolific participants represent the general population. And so, so we've done a lot of job trying to incentivize the actions that we want to see. And so that made it able for us to see the kind of stuff that we want to see, but then I don't have lots of observations about what people do in the real world. It'd be nice to collaborate with some, I don't know who's going to give us all the data. New York Times can give us the data if they want to. But I also thought about maybe I've been in talks with our school newspaper and trying to have a relationship where we create visualizations for them and then we can observe how people interact with the visualizations. So that might be a path where you can see more organic behavior. But I hesitate to generalize from any of these things that I showed you based on interaction, largely because these are still study settings. And so even when we go to the folks in the DoD, I mean, they're trained by, in this case, the Navy, and they're gonna do the work that you give them to do, right? They're way more disciplined, and so I'm not even sure the observations that we made that they're just gonna do the work is representative of a broader population as well as experts. So I hesitate to generalize from observations, but I know broadly speaking, the phenomenon of people not interacting, it's not just me who've seen that is like showing up a lot of different places.
I guess I'm kind of still thinking about what the role of like prediction is in these kind of systems. Like if it's highly predictive, like really like 100% predictive, does that somehow imply that the system or the visualization itself should be changed? Like at what point should you, I guess like what is the trade-off there? Right, like if it's poorly predicted, then you don't want to use it as a system, like the user shouldn't use it. If it's too predictive, I guess it kind of implies something about what the user are doing or what, I guess, like, how do I interpret?
So,
No, you tell me.
if you think about the goal of a visualization, the goal of a visualization
I don't know what the
isn't for me
goal
to
is.
predict what you're doing. The goal of a visualization is for you to extract data, depending on the scenario, but it's for you to learn something about the data. And if you're learning something about the data, then whether it's predictive or not is somewhat secondary.
But one could say, I guess, I'm just thinking out loud, right? Like visualizations is not just giving you a data set. You make very strong assumptions about what the user wants to do when you
Yeah.
decide to design a visualization.
Yeah.
And so there you're kind of trying to predict what the user wants to do. And so where is kind of like the,
Yeah, so I think it's like going into like my thoughts about like what is a visual analytics system, and so if it's simple and I'm like, if it's that predictive that you only have one path, then it's not really exploratory per se. But so I have lots of like competing thoughts in my head, because something can be predictive not because the visualization is simple, but because I have an idea of what you're looking at right now. So for instance, if you go to even the dashboard with lots of different components, and I see you looking at, say for instance, it's like a dashboard with lots of sales for a different company, and I'm seeing you looking at the map. The fact that you chose the map over all the different options tells me something that maybe you're interested in the geospatial location of different things. So I think it can be predictive and not necessarily because the visualization itself or this tool itself is simple, but it could be predictive just based on the context and what you observe. Does that make sense? But I do think that you make a good point about and this might be the difference between an information visualization that is meant to communicate something specific to you and a visual analytic tool that is meant to be more exploratory. And yes, I do agree that if you have a system that is meant to be more exploratory and instead is not, then it's not a valid visual analytic system. So I do see your point there. Yeah.
I had a question about the prediction algorithm. First of all, congratulations on getting something to work. It's not easy. But second of all, I guess if I understood it correctly, it was predicting kind of the next point or points that somebody would look at in the map. So it's very kind of next step and very localized. So there's probably a lot of locality information, although you did look at the type and the categorical information as well as the geospatial. What do you think possibility of going at a higher level of making predictions at the higher level goal, next goals versus this more spatial kind of next step?
This is something that has plagued me for several years now, because how do I know? I think it's possible if I know the space of all possible goals. And how do you then define the space of all possible goals? I've been thinking about it lately. I think it's possible under certain scenarios, but you need to know what that space is.
But isn't it also hard to get that articulation from the user? I mean, can you infer that just from the low level operations, or do you need them to say what they're looking for next, for example?
People that I've seen do that, they kind of like do it in, I guess. So what we're looking at just now in that specific scenario, I'm looking at interactions with data. A visualization system has more than that. So the work that I've seen had some success with looking at higher level goals and looking at things like action. Okay, I see you copy something, or I see you undo something. And so you're looking at now more higher level actions that can help imply something else. But I haven't seen work that could be potentially generalizable. I think it's a hard problem. I actually am like questioning, can it be solved? And the thing is, I don't know. I want, can it be solved in specific use case scenarios? Potentially, but I've only seen maybe one or, like, I'm thinking about some work that David Scott did a long time ago when he was at IBM. So they had some work that they successfully kind of mapped actions, and so these are actions like also someone's copy and like high level actions to higher level goals, but there aren't a lot of work out there, which I don't know if that is impossible or it is just a hard problem.
Yeah, I mean, I wonder if it's possible with just with the low level information versus having also like a way to detect the higher level, either through sense.
Yeah. We thought about doing like a more data-driven approach to this, but you need a large data set and yeah, I don't know. I want to do that. That's my next step because I really don't like that all I can do that. Oh, you're gonna might click on that next point. But it's hard.
It's good for prefetching.
Yes, I mean, Delani did some work where, so this is Delani, she did some work with prefetching, and that was more of a navigation task. And so, in that scenario, the space of actions are limited, so you can go up, down, left, right, zoom in, zoom out. And so the search space is small, and so it's more of like a target approach, like where you're gonna go next, so which trajectory, and less about why you might be wanting to look at this mountain and so on. So, but yeah. I like that. I mean, it's a challenge.
Definitely.
Any other questions?
Sitting on mine. So, okay, well, why don't we wrap up and thank Alvitta for the really, really interesting talk. Thank you so much.